Hello, good morning. Today we will cover 4 sections. Let me show you the discussion board first. Today we'll cover 6.3 very briefly. The detailed explanation can be found in lecture video for April the 2nd. Let me show you where that is. That's on announcement number 4. Okay, lesson number 8. Lesson number 8, the one for April the 2nd. And that will start from the 3rd hour, 22nd minute. Okay, so that takes how long? Yeah, that's approximately 25 minutes. Okay, please watch that one. I assume that you already watched that one actually. Okay, and then so it starts from the 22nd, the 3rd hour, 22nd minute on that lesson 8. Now, if you have not watched that one or you forget something, don't worry. I will just summarize that here later on and then do a couple of problems. But I will go over this 6.3 quite briefly. Now, after that, we'll move to 6.4. And that is corresponding to lesson number 9 in our announcement 4. And actually that day I cover only this one section. That day for the lesson 9, I cover only one section. So if you watch that video, lesson 9, watch before last week, supposed to be the material for last week. Okay, I only cover 6.4 for that day. Now, that day was a test day for my class. That's why the lesson only 2 hours. But that 2 hours, I spent the whole period on this 6.4. Okay, so I believe I give a lot of details on that already. You know. Okay, I believe I give a lot of details on that already. And then I will still give examples on this lesson 9, 6.4. I will spend approximately 1 hour on this lesson 9. And then I will go to chapter 7, chapter 7, the first part. Later on, I will introduce you to the situation first, and then go over 7.2. There's a chance I cover 7.1 after that, but let's take a look on the time. Okay, let's start with 6.3 first. 6.3 is on sampling distribution. And if you watch the video, that lecture video, you will see the following. Basically, the summary will be as the following. The summary, instead of saying that in long words, I use notation. Let X be distributed with the mean mu and the variance sigma squared. Let me put subscript X to explain that's from the standard normal, from distribution X. Now then, if we do sampling of size n, then the mean of this sampling distribution will be equal to the original mean. The mean of this sampling distribution will be the same to this mean. However, the variance of this sampling distribution will be equal to the variance of the original distribution divided by the sample size. Will be the same to this. Okay, divided by the sample size. Oops, I don't like that one. Divided by the sampling size. Okay, so suppose for example, we have a population whose mean is 100, and then the variance, let's say, is 2, maybe 25 squared. Okay, now then, if we do sampling distribution of size, let's say of size 7 from here, then the mean will be still 100. The same with this one. The same with the mean of the original distribution. However, the variance of the sampling distribution will be the original variance divided by the sample size. Okay, now consequently, of course, then the standard deviation of the sampling distribution is the original standard deviation divided by square root of 7. Basically, we do square root from here. If you apply square root, right, then the top becomes 25, the bottom becomes square root of 7. Okay. And just like that, just like that. Okay, now let's do some story. Let's do some story. For example, x be, let x be the number of passengers in a car going into a parking lot. And let's say we have the following. This with mean 0.7, the number of passengers, right? The driver is not counted, of course. The car can get into parking lot only because somebody drives, right? But there's a chance that it has passenger or it doesn't have passenger. And then the standard deviation, let's say, is 0.4. Okay, of course, I make up numbers. That's the standard deviation. Okay, now, if there are 50 cars in the parking lot, find the expected value of the sample, the mean number of passengers. So on average, okay, on average, how many passengers we expect from each car? The expected value of the mean, I think I need to, expected value of mean passenger sounds really wrong. Okay, the passengers are mean. No, that's not what I meant. Expected value of the number of passengers on average. So when we compute the average of number of passengers, then what do we expect? That will be the expected number of the average numbers of passengers of 50 cars. Then that will be 0.7. Notice that the expected value of the sample mean is basically the mean of the sampling distribution. And that is the same to the mean of number of passengers in a car. But here you see that if you have 50 cars, right? If you have 50 cars, then you expect some total number of passengers, right? Okay, now divided by 50, you will see that the expected number of passengers per car will also still be 0.7. The difference is here. Find the variance of the number, the variance of the number of passengers on average. Then the variance for the number of passengers on average. So this average number of passengers may be different from 0.7, okay? Give and take, right? Okay, maybe more, maybe less. Okay, but how will that vary? How will that spread? It will be the original variance divided by the sample size. Okay, so in this case, that will be 0.4 squared over 50. That's 0.4 squared over 50. Okay, therefore, the standard deviation for the average number of passengers will be 0.4 without squared over square root of 50. Now, do not underestimate this computation here. Do not underestimate this computation. We will use this in 6.4. In some textbook, like the textbook we use at West LA College, they actually combine 6.3 and 6.4 into one section. And it suddenly becomes a very big section, you know, and I don't want to do that either. Okay, I think the breakdown is best if we break it into two sections, like what our textbook's doing. So it discusses the sampling distribution first. Okay, but at least we have the following. So just in case, let's say that's the data we have from that parking lot. And then let's say just in a parking lot of a mall, let's say, or a grocery store. And then all of a sudden, for some reason, bad thing happened. There's an earthquake, let's say. Of course, we cross our fingers, it never happened, right? But suppose it happens, that there's an earthquake, okay? So because earthquake happened, how many people do we need to find? Alive or not alive? So you have the data from the past. We know that the mean is 0.7 and standard deviation is 0.4. Now, suppose you have 50 cars, then how many people you expect? How many people you expect to be in that grocery store that use that parking lot? Okay. How many people do we need to find alive or not alive? So of course there should be 50 drivers, right? Plus how many passengers? Okay, simply because 50 people show up saying that, oh, we are actually, we came to this mall or to this grocery store by car, parked in the parking lot. Simply because we find 50 people, will you be happy? I don't think so, because these 50 people, part of them may be driver, but maybe passengers. It means there are some drivers not found yet and some passengers not found yet. Okay, so how many people should we find? And at what number should we stop saying that, hey, you know what, I think we have enough? Okay, that's the question, right? Okay, now then from this data, we see that the expected number of average passengers on average is 0.7. Okay, so the expected number of passengers in total should be 0.7 times 50 cars. That's 35 passengers we expect. Okay, so we need to find 85 people, give or take. Okay. Now, how many more should we look for? That's something we learned in 6.4. But for now, at this point, we say, you know what? We need to do searching for 85 people. When do we stop, Thomas? If we have approximately 85. Will we stop at at 80? Maybe, but that's something we will compute in 6.4. Okay, now the use of this thing here, the variance and standard deviation, will become very significant in the next section, 6.4. Okay, now let's do one more example before I go to the next section, 6.4. Example 3. Let X be number of tails in tossing a coin, let's say 40 times. Probability to get a tail is, let's say, 0.6. Now we know if we have this kind of experiment, you toss a coin 40 times, the probability of tail is 0.6, then the number of tail will be binomially distributed with mean 40, probability of a tail is 0.6, right? That's 5.2 or 5.3. 5.3, I believe. No, 5.2. That's binomial distribution 5.2. Okay, so from there we see that the mean is n times p. That's 24. And the variance is n times p times q. Okay, that's 9.6. So that's the distribution of the number of tails when you toss the coin 40 times. Okay, now someone, let's say Tom, repeat this experiment of tossing a coin 40 times. Okay, now Thomas repeats this experiment. Let's say I repeat that 12 times. So Thomas did a total of 12 times 40 tossing. Okay, now then find the average number of tails in each experiment. So you do this experiment 12 times. Okay, you do the experiment 12 times. What is the average number of tails per experiment? So you get the total number of tails you get divided by 12. Okay, now according to our theorem, sampling distribution, according to our lesson, the average number of tails in each experiment will be equal to the average number of tails for that binomial distribution, which is 24. Okay, basically, Tom expects a total of 12 times 12 experiments times 24 number of tails each experiment. Okay, that's 288 tails. Again, Thomas tossed it how many times? Thomas tossed it 40 times each experiment times 12. Okay, so you can imagine it this way. So Thomas do it 40 times for each experiment. Now the thing is, like, he does it 12 times. He does it 12 times. Now the average for each is 24. The average for each is 24. So the average of this average will still be 24. Okay. Now, how about find the variance? Find the variance for the average number, I think I should not, I should not say it that way. Find the variance for average number of tails, that's right, in each experiment. Now, we expect the average for each trial to be 24, right? The number of tails to be 24. But in reality, the average may be the number of tails may be 24, maybe 25 in the next experiment, maybe 26 in the next experiment. Okay, so it's 24 give or take, right? Now the thing is, how will that vary? How will that vary? Do you expect that all of a sudden you have one experiment where you toss the coin 40 times and all of a sudden none of them tail? It's possible, but the probability is so small, right? Or in the other experiment of tossing the coin 40 times, and suddenly all of them tails. But that's possible, right, Thomas? Yes, that's possible, but the probability is very, very small. Okay, now of course, then because of that, the variation will be much less, and the variance will be the variance for the number of, I should say, number of tails in each experiment will be the original variance divided by n. In this case, the original variance to 9.6 divided by 12. That's 0.8. Therefore, the standard deviation of the expected number of tails for each experiment will be square root of 0.8. Now again, the variance for the number of tails for each experiment is something we can explain better after we do 6.4. But for now, at least we get this thing. Okay, at least that's what we get. Now, I did say that 6.3, 6.4 sampling distribution and central limit theorem are very, very closely related. And a lot of part of 6.3 can be explained better in 6.4, but I still prefer that these two sections are separated. In 6.3, basically, we learn this thing. That's basically what we learn. Okay, and the thing is, this is true for every situation. It is true in general, always true. Okay, as you can see that if you do the experiment one time with this mean and this variance, then when you do the same experiment n times, then the average, the expected number of mean will be the same with the original one. Yet the variance of that mean, the variance for that mean will be smaller. You see, it gets smaller. Okay, now let's go to 6.4. I see the suggested our textbook on 6.3. Instead of the exercise from 6.3, I see that they want you to do a lot of experiment, and that actually takes so much time. So instead of doing it that way, let me just go on to 6.4. After all, that's where we will use it. Okay, now what is 6.4? Central limit theorem. This is one of the building blocks for probability and statistic. Okay, so if people ask me, what is the building block of probability and statistic? The cornerstone. Okay, the first one is normal distribution, standard normal distribution. That's the first one. And then after that, you will have central limit theorem. Okay, that's the one building probability. From these two, you have probability and statistic becomes very, very big, like right now. Okay, without these two topics here, probability and statistic actually get stuck for many years, for many decades, if not centuries. Okay, but with the invention of central limit theorem, it starts from normal distribution and therefore central limit theorem, then all of a sudden statistics become a topic that is very, very big and very useful. Now, what is central limit theorem? Central limit theorem consists of two parts, but the first part is the crucial one. The second part basically mimic the first one. The first part says the following. If you have a random variable that is normally distributed with mean mu and variance sigma squared, then the sampling distribution, the distribution of the sample mean of size n, will also be normally distributed with the same mean, and the variance is the original variance divided by n. Maybe I write it this way shorter. This is the mean of that sampling distribution, and this is the variance of that sampling distribution. Okay, now from 6.3, we already learned that if you have a distribution, a random variable whose mean is mu and variance is sigma squared, then the sampling distribution of sample mean will have the same mean. Okay, we'll have the same mean and the variance will be, the variance of the sampling distribution will be the same variance divided by the sample size. Now, we learned that from sampling distribution. What is new here is the fact that if the underlying distribution is normal, then the sampling distribution will also be normal. Okay, Thomas, I don't understand your notation. Okay, if you don't understand my notation, feel free to see how our textbook actually explain it. Describe that central limit theorem. Okay, let me show you. Let me see how our textbook actually say it. Sometimes it's just like, do you like to write it in the small, very short summary, or do you like it to be wordy? Okay, so this is what our textbook actually says. Just for that part one, I say that central limit theorem has two parts, right? Okay, now central limit theorem has two parts, and this is the first part. That's long, you know, that's long. Just to explain that central limit theorem, they require this long explanation here. You know, in other words, you cannot run away from notation. Okay, however much you don't like notation, okay, trust me, you will hate wordy explanation even more. Okay, no, there's no shortcut for that. There's no shortcut for that. I'm sorry. Okay. I did hear people actually say to me in the past, Thomas, I don't like notation too much. I said, well, when you read the book, you get it. Okay, well, I don't get it either. So you don't get it either way. You don't blame it on me. Okay. Another one is this. This is strange. This is strange. Okay. Have you, I mean, it is normal though, me included. A lot of students don't like word problems. And I agree with you, including me. Now, a lot of students don't like word problems. It's one thing. Now, it is another thing when somebody say a lot of students don't understand Thomas Wood's problem. Don't like. As if they blame it on me. Thomas, I don't understand your wording. Trust me one thing, I know that I'm not a native speaker, even though I can actually almost guarantee you that my grammar is much better than a lot of students here, because for me to go to graduate study, I need to take TOEFL, if you know what is TOEFL, okay, and TOEIC. TOEFL is test, I forgot what TOEFL stands for, but it's basically if you're a foreign student and you want to go to, university in the United States, one thing they ask you is to score well in TOEFL. Okay, you need to take TOEFL to see your English background. Are you well prepared? Okay, and you need to be really good with your grammar here. Now, and then I also need to take what they call TOEIC if you want to teach. Okay, so in TOEIC, we basically need to balance not to use way too technical words when we teach, but at the same time, try not to get too far away from the actual meaning. In other words, you still need to say things right. You see, you can't just say, oh, Thomas, that's what people understand, and suddenly you don't use a standard terminology anymore. No, we still need to say things right, but try our best to say things in a way people understand. But that also means that we do require students, our listener, our student, to know some English. Okay, now, There are some students, actually a couple students actually filed formal complaints against me in the past, which I don't mind. Okay, they say that Thomas word problems is very hard to understand. And for me, that's kind of discrimination though. It's just like simply because I'm not a native speaker, does it mean that my English is worse than you? Okay, it's two different things. Simply because I'm not native speaker doesn't mean my English is worse than you. Okay. These are students who never even passed English 101, and they're dare enough to tell me that their English is better than me. Okay. And how do we know that their claim is true, that Thomas word problems is confusing? Okay. There are two things you need to do. Okay. Apply Tom's question, of course, not only to them, but two different set of students. Students who take my class and students who took somebody else's classes. Okay. And for these same students, ask them to take word problems from other teacher also. So besides taking tests from Thomas, take problems from other teacher. And then do word problems from other subject. It doesn't have to be math. Let's say psychology. It turns out that the students who say that Thomas test is confusing also get confused with other teachers, native speaker, and also not doing well in other subject when it comes to reading. Basically, these students who say Thomas word problems is confusing is confused whatever they read. Okay, it's like they say that they don't understand Thomas word problems. Okay, fine. Can you read other things? Well, I don't understand those too. So basically, you don't know how to read. Your reading comprehension is so low, but you blame it on the person who may give you the reading. No, that's not right. Okay, I don't mind to be criticized. And because of that critique in early of my career, when it comes to word problem, I'm quite careful. Instead of writing the question myself, I actually copy paste from other people's tests. Usually I copy paste from other university. Okay, most of the time I copy paste from problems at USC. Okay, the wording will be the same. I change the numbers here and there. Okay, or from UCLA, UC Berkeley, MIT, Harvard, UC San Diego, University of Washington, and yeah, there are a lot of problems you can find on the internet. Okay, such that for those students who say that, oh, Thomas, I don't understand your wording, I will just reply that person, you are just not USC material. Bang, that's it. Okay, why? Because the wording's not from me, that's from USC. The wording's not from me, from UCLA, from Cal Poly Pomona, for example. Okay, so you see how I use statistic to go against people who complain against me, right? Okay, so yes, the claim is Thomas wording is confusing, fine, okay? But to know that the problem is with Thomas or not, you test this person, or these people also, using problems from other teacher, okay? So if this person, these people who complain against Thomas wording is confusing, if they take tests from other teacher and they are doing well, it means they understand the statistic, but Thomas wording is bad. Okay, but if they don't understand problems from other teacher, but they do well in other subject, it means they don't understand the statistic, but they are pretty good with their reading. Okay, but what if even in other subject they don't do well? Well, this person is just complainer. Okay, now I'm not trying to corner these students though. I still trying to update myself when it comes to wording. Okay, that's a skill I still keep on learning. Okay, what I want to tell you is this: if somebody complained against you, not only in this case, like somebody complained against you in your work, right? Okay, one customer complained against you, then your manager, or let's say you are the manager and some people complain against one of your employees, right? Okay, so this customer don't like Thomas. Let's say Thomas, your employee, and this customer don't like Thomas. Okay, see what happened to other customers. Do other customers complain against Thomas in the same case? Okay, and so if it is yes, other customer complains against Thomas in the same case, then very likely it's Thomas' fault, right? But then you see what happened to other employee. If other customers complain against other employee at the same time, then it is structural. It's not only Thomas' fault. Okay, so complaint against Thomas, one complaint against Thomas from one client. Is it also complaint against Thomas in another client? That's if you want to detect if that's Thomas' fault or the client's the one don't like Thomas. Okay, but also you see another client or maybe the same client against other employee. Because it is possible Thomas actually just run the standard operational procedure of the company, and that SOP, standard operational procedure, is the one at fault, right? Okay, so how do we solve a problem? This is not just about complaint. It's about, like, if we see a problem, how do we solve that? Instead of just pointing fingers at, oh, what should be done? Okay, now it is all come from this thing that we talked about earlier. Would you like notation or words? It's not easy choice. Trust me. If it is easier for me to write it in words, then I would have done so. But the thing is, that's not the case. In the end, we summarize that to this. If the original distribution is already normally distributed, then the sampling distribution of size n will also be normally distributed. What happened to the mean? The mean will be the same with the original distribution. What happened to the variance? The variance will be the same with the original distribution, the variance of the original distribution, except that you need to divide it by the sample size. Okay, too many colors, huh? Oops. Oh, that's the first part. The second part, which gives us the same conclusion, is the following. Let original distribution is not normally distributed, or let's say unknown to be normally distributed, but the mean is known, the variance is known. Then what happened with the sampling distribution? The sampling distribution will have the same conclusion. It will also be normally distributed with the same mean and variance, original variance divided by n, as long as the sample size is at least 30. Okay, so for the first case, it's for any sample size. As long as the underlying population already normal, then the sampling distribution will be normal. Now, what if the original distribution is not normal or unknown to be normal? Then we require the sampling size to be at least 30. Okay. Now, let's do a problem from our textbook to clarify what we learned. Maybe my example first. Let's say, for example, let X be normally distributed with mean 100 and variance 15 squared. Or standard deviation is 15, therefore the variance is 15 squared. Now then, what can we say how will X bar 15 be distributed? If the original distribution already normal, then even if the sample size is less than 30, the sampling distribution will still be normal. Okay, the sampling distribution of size 15 will also be normal with mean 100 and variance, the original 15 squared divided by this 15 here. So they happen to be just the same 15. Okay, the mean comes from here. The variance comes from here divided by that sample size. That's it, that's simple. Okay, now let me do variation from this example 1. Let the IQ score of adults be normally distributed with mean 100 and standard deviation 15. Now part A, find the probability that a selected adult, a randomly selected adult, has IQ score more than 110. That's what we learned in last week, right? Last week. So X is normally distributed, right? Let X be the IQ score of one adult. Let X be IQ score of an adult, only one adult. Now we know that this IQ score will be normally distributed with mean 100 and standard deviation 15, so that the variance is 15 squared. Now, what is the probability that X is more than 110? And this will be normal CDF, lower bound 110, upper bound infinity E99. The mean is 100, standard deviation 15. Let me remind you, this is the lower bound, this is the upper bound, this is the mean, this is the standard deviation. Now let's use calculator. How to compute that? Second distribution normal CDF. The lower bound is 110. The upper bound is E99. The mean is 100. Standard deviation 15. The probability is 0.25249. That's 0.25249. That's the probability that one randomly selected adult has IQ score more than 110. Now, we change the problem, find the probability that, let's say, 9 randomly selected adults have mean IQ score, average IQ score. So the average of these 9 adults more than 110. So not only one adult right now, now we have 9 adults. The thing is, we want to find the average IQ score of these 9 adults. According to central limit theorem, it will be normally distributed with mean 100, the same mean with the original distribution. Oh, this is the original distribution. Okay, that's the original distribution. This is the mean, the same mean with the sampling distribution. Okay, but the variance will be the original variance divided by sample size. The original variance divided by sample size. That's how it is distributed. Now, therefore, from here, we can compute further. Then what is the probability that the sampling distribution, the sample mean of 9 adults will be greater than 110? That is normally distributed. So we will compute that using normal CDF. The lower bound is 110. The upper bound is E99, which is infinity. The mean is 100. The standard deviation is 15 over square root of 9. Okay. Then when I use my calculator, oops, sorry, not this one. When I use my calculator, am I sharing the correct one? When I use my calculator, that will be normal CDF, lower bound 110, upper bound E99, the mean is 100, but the standard deviation will be 15 divided by square root of 9. 0.02275. So to find only one person with IQ score more than 110, the probability is like around 1/4, is 25%. It's approximately 1/4, is 25%. Okay, but to have 9 people randomly selected and their average IQ score is more than 110 on average, the probability becomes only 2.3% approximately, 0.02275. Okay, pictorially, if we deal with only one person, it is normally distributed with that mean 110. I'm sorry, the mean is 100. The probability to be more than 110 will be like that. Now, But because we are dealing with sampling distribution X bar, the mean will stay the same. The mean will stay 110, but the curve becomes very skiddy. And to get 110 or above, the probability becomes small. Okay, that's the distribution for X bar. That's what actually happened. That's what actually happened. Okay, let me circle this picture, make it smaller, and squeeze it in there. Okay, now let's do a couple problems from our textbook. I believe I did even numbers before. Let's do odd numbers right now. Give me a second. Let me screenshot this number. Hold on, not this one. I will start from here. Number 5, using central limit theorem. In number 5 and number 8. 5 to number 8. Assume that females have pulse rate that are normally distributed with mean 74 beats per minute and standard deviation 12.5 beats per minute. Okay, so let's define a random variable first. Let X be the pulse rate of a female. Then according to the passage, this pulse rates of a female is normally distributed with mean 74.0. That's the mean. And the standard deviation 12.5 per minute. Okay, now then number 5A. If one adult female is randomly selected, find the probability that her pulse rate is less than, I don't need to use XS here. Find the probability that that pulse rate is less than 80 per minute. That's the probability notation. The calculator notation will be normal CDF. Negative infinity is the lower bound. 80 is the upper bound. The mean is 74.0. Standard deviation 12.5. Okay. Now I hope you can compute that. I will let you compute that later on. Okay. Now let's see part B. Part B. If 16 adult females now randomly selected, find the probability that they have pulse rate with a mean, the mean of the 16 pulse rates from these 16 females will be less than 80 per minute. So X bar 16, that's what we want, right? The pulse rates average of 16 adult, 15 females. I keep on saying adult females because I have a daughter. She is only 15 months right now, but her pulse rate is actually definitely much higher than 74 per minute. It turns out that babies, toddlers have heart rate much higher. You know, their heartbeat actually beats faster. Then according to central limit theorem, because the original distribution is already normal, then the sampling distribution will also be normal. Yet even though the mean is the same, 74.0, the standard deviation will be different. The variance will be divided by the sample size. Therefore, the standard deviation will be the original standard deviation divided by square root of the sample size. Okay, now then part B, probability notation, probability that the average pulse rate of 16 female is less than 80 will be normal CDF, negative E, 99, 80, 74.0, that's the mean, and standard deviation is 12.5 over square root of 16. Okay, now let me ask you to compute that. Use your calculator, compute that. I want you to compute these two things here. I want you to compute part A, what is this here, and part B, what is this here. Okay, please do so. Let me give you 2 minutes for that. So according to my calculator, normal CDF for part A, the answer is 0.68439 if I round it to 5 decimal places. And for part B, I get 0.97257. Now please confirm that's what you get. Okay. Make sure you know how to set up the situation. Part C, why can normal distribution be used in part B even though the sample size does not exceed 30? Well, because the underlying distribution which is X is already normal. Okay. Now, using the same question, let me ask you to do the following problem. Number 7. Okay, with the same informations. We use the same informations. Let me copy that down here. That is, X is normally distributed with mean 74.0 and variance 12.5. So the 12.5 squared. So I would like you to do part A and part B. Very similar questions. Maybe 4 or 5 minutes. So I will come back at 9:34 or 9:35, but I want you to do these problems. Okay, let's start. So part A, what is the probability that a randomly selected adult female, that's X, has heartbeat between 72 to 76 beats per minute? That is normal CDF, lower bound 72, upper bound 76, the mean 74.0, and then the standard deviation is 12.5. And according to my calculator, that will be 0.12814. Now, part B, if you have 4 adult females instead, find the probability that they have pulse rates with a mean between 72 to 76. Probability that X bar 4 will be between 72 to 76. Okay, now notice that X bar 4 will then be normally distributed with the same mean 74.0, but the variance will be 12.5 squared over sample size 4. Okay, so the standard deviation of the sampling distribution will be 12.5 over square root of 4. Now then, this will be normal CDF. The same lower bound, the same upper bound, the same mean, but the standard deviation will be the original standard deviation divided by square root of the sample size. That gives me 0.02529. Now, why we can use normal distribution while the sample size is not 30? In part C, I didn't ask you to do this one. Well, because the underlying distribution X is already normal. Okay, that's for number 7. Let's do a couple more problems from our textbook. This time, let me do a harder one, or maybe slightly harder one. Okay, let's see number 13. You don't like word problems, right? Let me pick up questions from the book then. The problem with problems from our textbook, even though they are grammatically okay, but they are way too wordy. It's like for you to read this passage only will take you at least 5 minutes, maybe. Okay, that's why I try not to pick problems from our textbook. And some students like to make that comment, strangely though. Thomas, your problem is so different from textbook. I say, do you really want me to give you problem from the book? That's what it looks like. Okay, I mean, be careful with what you wish for. Okay, no. I try to get to shorter type of questions, like more brief, okay, and still easy to understand, okay. And for a lot of reasons, our textbook may not be a good source. It is still a good one if you do that as an exercise at home, where the time restriction is not that you don't have time restriction, right? But if I put this question in your test, I don't think that's a good idea. I mean, I don't want it. Okay, as a student, I don't want this kind of question. Okay, not because it's hard. I don't even read it yet, so I don't know if it's hard or not. It's just like too wordy, right? Even if I can understand the wording, it still takes me some time to understand it, right? Okay, because it's too long. Okay, but let's see. Passengers died when a water taxi sank in Baltimore Inner Harbor. Men are typically heavier than women and children. So when loading a water taxi, assume worst-case scenario in which all passengers are men. Assume that the weights of men are normally distributed with mean 189 and standard deviation 39 pounds. So let X be the weight of a man, one man. This X is normally distributed with mean 189 pounds, standard deviation 39. So this is 39 squared. That's a big standard deviation, by the way. Now, the water taxi that sank had a stated capacity of 25 passengers, and the boat was rated for a load limit of 33,500 pounds. Okay, now part A. Given that the water taxi that sank was rated for a load of 3,500 pounds, what is the maximum wind weight of passengers if the boat is filled to the stated capacity of 25 passengers? So part A. So the load limit is 3,500 pounds. Okay, and the number of passengers is assumed to be 25, the maximum stated capacity. So what is the maximum mean weight? That will be 3,500 divided by 25. That will be 140. Okay, so if the load limit is 3,500 pounds, and they say up to 25 passengers, it means if you really have 25 passengers there, then the maximum mean weight for these 25 passengers should be only 140 pounds. Okay, the problem is in part B. If the water taxi is filled with 25 randomly selected men, what is the probability that their mean weight exceeds the value from part A? So the average of 25 men will be normally distributed with the same mean 189 of the underlying distribution, right? Okay, but the standard deviation will be, I'm sorry, the variance will be 39 squared over 25. Notice that the standard deviation actually is smaller, okay, not bigger. If the weights of men has variance 39 squared, standard deviation 39, then the mean weight of 25 men will have standard deviation 39 divided by square root of 25. Okay, so what is the probability that the mean weight of these 25 men is more than 140? We can also see it this way if I relate that to part A. Okay, suppose you have 25 men on that boat. What is the probability that the total weight is more than 3,500? Well, if the total is more than 3,500, then the average must be more than 140. So you imagine the total divided by the number of people. That's the average, right? The average is the total over the count, remember? The first day of class. So I divide by the count, 25. That's how we get that. The mean of 25, the mean weight of 25 men to be more than 140. Okay, so the probability will be normal CDF 140, that's the lower bound. Upper bound is E 99. The mean is 189. And standard deviation 39 over square root of 25. And that's 0.99, oh, basically 9999999, a lot of nines. That's basically 1. So the probability that the total weight is already exceed the capacity is 1. For sure, it's already. Basically, if you happen to have 25 men getting into this water taxi is guaranteed to fail. Okay. Now part C. After the water taxi sank, the weight assumption was revised so that the new capacity becomes 20 passengers. So the new capacity is now 20. So N now becomes 20. If the water taxi is filled with 20 randomly selected men, what is the probability that their mean weight exceed 175, which is the maximum weight that does not cause the total load to exceed 3,500. So what is the probability that the total weight is more than 3,500, which means the probability that the mean of these 20 men, the mean weight of these 20 men is more than 3,500 over 20. That's how we get 175. That's how we get that 175. Okay, now then this will be normal CDF, lower bound 175, the mean upper bound is E99, the mean is 189, standard deviation is 39 over square root of 25. I'm sorry, square root of 20. Because the average of 20 men. Okay, now that will be 0.945795. So that's 80. That's the probability that 20 passengers have the average weight more than 175. Therefore, the total weight is more than 3,500. That's approximately 95% chance of overload, right? The total load exceed 3,500 pounds. Is the new capacity of 20 passengers safe? The answer is no. It's not safe. What happened if all of them women, Thomas? Then take a look on the average for women. Okay. Take a look at the average of women. Okay. Now, I think this is the situation though. You know, like a boat, the heavier it is, the further it gets into the water, right? So they're supposed to put a line. This is my suggestion. They're supposed to put a line where if this line, or maybe they color it red above that line. And maybe I put it this way, my bad. Maybe they color it this way. Sometimes it's hard to argue with people too, right? So imagine if you have a supervisor or somebody who monitor if the capacity is already overload or not. It's kind of hard to tell people, hey, you know what? This boat is overload. This water taxi is overload. You know, okay. Sometimes they don't want to listen. Okay, they just go. That's fine. We are safe, right? Then they're supposed to. They may. This is just suggestion. Okay, so let's say the boat is safe as long as you see the green. Okay, but if you put more and more people into the boat, then it gets to the yellow one. Now, once it gets to the yellow one, you start telling, hey, you know what, stop. It's already yellow. Okay, it is safe for now, but if we have some big wave, it may not be that safe anymore. Okay, but once it is already over capacity, then the boat will go deeper into the water and it will show only red. So they may want to consider coloring the boat this way. Okay, so instead of arguing with those passengers who usually the tourists and they, I mean, I like to go around too. Okay, and sometimes once I get to the boat after getting in line for so long, I don't want to yield. I want to stay in the boat. Oh, it's dangerous. Just a little bit. That's okay. Let's go on, right? Okay, but of course, I as a passenger only go to that place once, but the person who operates the boat will take the consequence if anything goes wrong. Right. So my suggestion to the operator, color their boat this way. Okay. So, and put a mirror. Okay, so that the passenger can see what kind of danger they are actually facing. Okay, they may want to color some part of that to be black also. Okay, such that if you want to go, if you want to die, make it the water go that deep and then let's sail. Right? Not a good idea though. Okay, it's just a big no-no. It's a big no-no. Like once it gets to that color, then the operator should leave the boat. Okay, ignore the boat before you sail. Because once you sail, the captain is supposed to be the last person leave the boat. Okay, so before the boat leaves the harbor or the the station, then the captain is supposed to leave first. So, okay, it's not sailing yet. So I have my right to leave the boat, right? It's out of my hand. You guys just don't listen. Okay. That's actually a form of responsibility though. You know, sometimes like people don't want to listen, then what do? Instead of arguing with them, just ignore them, walk away. There's no need to, sometimes there's no need to talk to people who don't think. If they're already by their emotion, right, just walk away. I mean, the more we talk, the more things they will use against us. You know, they will pick and choose what we say. You say, I say case thingy, you know. Okay, even though I think I don't really get complaints in the last, I think in the last 7-10 years, I get only 1 or 2 complaints, maybe like formal complaints that goes very far. But I usually help my chair at West LA College for complaints against other instructors. And honestly, some of them are just ridiculous. Some of them are just ridiculous. Like one of the most common complaint is this though. The professor never said that we have a test on which day. Okay, and it turns out that the test was already announced, the date of the test already announced in the syllabus, and the student hardly show up in class. And even if the student show up, they show up late. So even when the instructor remind them about the test, strangely, they won't be able to hear that because they was not there yet. Okay. Anyway, this is just a suggestion from someone who don't have experience in water taxi thingy. Okay. So my suggestion may be absurd, maybe ridiculous. Let me just erase it. Okay. I'm about to give you a break, but during this break, let me ask you to do more problem. We have actually pretty good problems here. Let's see. Number 17 is way too long, in my opinion. Maybe number 19. Yeah, maybe number 19. I don't think I did number 20 though, but let's do number 19. Sorry. Let's do number 19. Doorway height of Boeing 757-200ER. I don't like that. I mean, I more or less follow. I more or less follow the airplane history construction thingy. Okay, this ER stands for extended range. Extended range. So what happened is they have the original 757-200. Okay, they have the original one. They call that 757. That's for the type. The 200 for 200 passengers. Okay, but then they modified the wing a little bit. Okay, they modified this and that a little bit such that this plane can actually go further distance. Now, usually for 200 passengers, they just design it for local, domestic flight. Let's say from LA to New York, LA to Florida, like that. Okay, but the reason they want to do extended range, because if they add just a little bit more fuel, let's say, and if they can save the burn rate of the fuel a bit, let's say by extending the wing a little bit, they may be able to fly, instead of 3 hours, they may be able to fly 4 or 5 hours. You see? Okay, so they may end up going to, let's say from New York, be able to go to maybe German. I don't know. Okay. So that's why the reason they do extended range is because they want to keep the capacity Usually international flight, the capacity is higher, like around 300 passengers. But you may be able to do only 200 passengers if you have the the tank is big enough, okay, and you want to have more frequent flights. Okay, so this turns out to be more economic for the airline company. Now, then the height has the doors of height 72 inches. Now, heights of men are normally distributed with a mean of 68.6. So let X be the height of a man. Now this height is normally distributed with mean 68.6 and standard deviation 2.8. So the variance is 2.8 squared. So part A, if a male passenger is randomly selected, find the probability he can fit through the doorway, which is 72 inch, without bending. So what is the probability that a randomly selected male has height less than 72? Only one person. Okay, part B. If half of passengers are men, so N is equals to 1/2 times 200 passengers, that's 100 passengers, right? Find the probability that the mean height of the 100 men is less than 72 inches. So find the probability that the average height of these 100 men is less than 72 inches. When considering the comfort and safety of passengers, which result is more relevant, the probability from part A or the probability from part B? Which is more relevant? The comfort and safety of one person or the average? Or the average? Okay, simply because the average people actually feel okay with that, will that be safe enough? And you will see that is actually not true. Okay, the consideration is like, it's like this, it's like this. In the end, I'm talking about the general case, not only for safety, not only for that airplane, also in teaching, also in providing service to people in general. Okay, you may have 100 customers. You may have 100 customers and you provide good service to 99 of them. But the one give you headache is the one that you don't provide good service to. Okay, and this one person may be the one who actually posted on Facebook, on Yelp, or some mass media complaining against your service. Okay, so it's not about what most people feel, because if they feel good, if they're satisfied with your service, there's a big chance they don't say anything because they think they deserve it. They are paying customers. And it is rightly so. Okay, it is rightly so. Okay, it's this one person complaining is the one that give you a lot of headache. Okay, now I'm not saying that if you are complaining, it's you are a headache. No, that's not what I'm saying. In regard of this question, I want to say that it's not about the majority. It's just about some people that feel discomfort during the flight or during your service, that give your company a bad impression. Okay, so please don't think because in average people are okay, then you can just ignore the need of one or two people. No. Okay, in other words, especially in America, by the way, our political system here, if you think about it, it's not democracy. It is the form of our governments is actually republicanism. I'm not for the Republican or saying this to support Republican Party. No, No, that's not what I'm saying. What I'm saying is the form of our government, and therefore how the administration or how this country being run is that minority is protected. Okay. So you cannot be both. You cannot be both. You cannot say that you are for democracy and at the same time, then you want the minority to be protected. Okay. Because democracy basically means majority rules. If the majority wants to go against the minority in democratic system, majority wins. But that's not what we want. And that's why America is actually such a great country. I am happy to stay here because even though in case I am not majority, even though in case I'm minority, I know the law protect me. Okay, now this becomes the hope for people who come to America because our form of government is republicanism where minority is protected. Okay, simply because the majority, of course, rules, okay, but it is the law protect the minority such that the majority do not put too much burden on the minority unreasonably. Okay, for example, I'm Indonesian. Okay, and even though I'm Indonesian, I'm US citizen, and it's not about my citizenship though. But as an Indonesian in America, of course, I'm minority, right? Okay, but why I feel happy and satisfied with living in America? Because even though I'm minority, my rights are protected. Okay, find a country that is better than America, and you can move to that place. Okay, now we have a lot of things we have to fix in this country. Okay, and I hope we do our part. Okay, I hope we do our part. I'm not saying that America is without problems. We have problems. We have a lot of problems. Okay, but compared to other countries that I can think of, this is still the best country for me. Okay, now this may not be the best country for some people, and that's totally fine. You know, okay, find a better place. And no offense, no offense, no offense. Okay, I just feel like if you think this country is not best for you, why don't you move to a better country? That's one. Okay, or if you want to stay here, what do you do for from your part to fix it, to make it a better place? Now, I'm saying this not because not by just saying that. Okay, I want to show you something before we go to break with this question. I want to show you something in which I believe you saw that also in my videos sometime in the past. And something I proudly share. Okay, maybe I just say that instead of login, so on and so forth. Okay. What I do that I'm proud of sharing with you, not to brag, but to show you that I'm a human. There are things that I don't do well, okay, and you should not follow. For example, gambling. Okay, don't follow me on that one. Okay. Sometimes I don't treat my wife well. That's not something you want to follow. Okay, but I think a lot for my wife. So I prepare in case of my demise, in case of my death. They are fine. That one I want you to follow. Now, beside that, I also donate platelets. I drive for American Red Cross. They need driver, by the way. So what happened is the blood that being processed by Red Cross, they are all being processed in the big processing facility. In LA, it is in Pomona, next to Cal Poly Pomona. Okay, and then from there, they drive the blood to a lot of hospitals. They drive the blood to a lot of hospitals. So it is not from, let's say, you donate your blood at West LA College, and then from there they bring it to hospital right away. No, they need to go to the processing facility first, being tested if it is okay, being separated for this and that, and then they bring this to the hospital that need. Okay, now the thing is, to reduce costs, they need volunteer drivers. And I actually volunteer to drive for them. Okay, but we have to say that most of the time they still depend on basically the delivery service, for which they need to pay, and they need to pay more. They need to pay more, not just like paying like a regular taxi. No, they actually need to pay more, because these taxis, right, the delivery service, need to have certain specification for them to drive blood or platelets. Okay, now to reduce costs, they ask for volunteer. Other thing I do, I donate my money. Besides paying tax, right, which I consider that a donation to US government, okay? So I also donate my money to, for example, LA Mission, okay, Union Rescue Mission, to World Vision, at the amount of approximately $4,000 a year. Now, I'm saying this to you not to brag, you know what, I donate a lot of money. No, no. I want to give you an example, right? Hey, you know what? Once you are rich, once you have some money, don't forget that people out there need our help. And you don't need to be rich, actually. You need to feel content with yourself. Okay? If you keep on saying, I need this, I need this, I need this, I need this, then in this society, in this community, you are basically just a sucker. You are the one need to be satisfied all the time. Okay? How about you become a problem solver? There are really people out there that need your help. Okay, can you give part of what you have for them? Okay, now sometimes it's been a long time, I don't do that since pandemic especially, but sometimes I actually went to Union Rescue Mission and then just help with the food there, serving the food, okay, to homeless people. Okay, make them feel that some people still willing to serve them and help increase their confidence, their feeling of dignity. Okay, you can do that little part. Okay, it's just about donating your time. It's not donating your money, right? And I also donate to World Vision for International. I currently support 9 girls, and purposely girls from third world country where girls are basically the third or even the fourth class in the society, like adult men the first, and then boys the second, adult women the third, and small girls the last in the society. I mean, they are the one who get the least attention. I support 9 girls from some countries such that they have enough support, at least financially, for their health, and guaranteed they go to school, okay, and they have enough food. And I support them until they get their elementary school diploma. Unfortunately, I want to support them actually up to they have their high school, but World Vision does not allow that. So beside that, I support some other people in Indonesia, because that's the only channel I have, so that they can finish their university. Up to now, I already support 4 students to finish their university back in Indonesia. And actually, I want to say that 2 students, one of them in UC Riverside, almost finished. his bachelor, and he just told me a couple of days ago that, Thomas, you know what? I will go for master's degree. The school will pay for my tuition. I will have issue with food only, but hopefully I can work on the side later on so that you don't need to support me anymore. I also support 5 orphanages. Not a lot though, not to the point that I'm the only supporter, just a little bit of me. 5 orphanages. That's what I do. Okay, of course, sometimes my wife not happy that, Thomas, you spend too much time for other people, but not for your wife. You know, and my answer is that, hey, at least you live with me. What I enjoy, you enjoy also. But how about these people? You know, sometimes they don't even know where they need to live the next month. Okay, so that's what I share with you. Not to say that I'm a perfect person, but I do my part. Have you done your part? Instead of just demanding other people to satisfy your need all the time. Okay. I mean, you have your need, and of course we do expect other people to help you, right? But do you do your part, at least right now, study, such that one day you can be the one who support people around you, okay? Now, it all comes from America, minorities protected. In the past, back in Indonesia, we have a very strong democracy there, in a sense that majority rules and overrules, such that, as for example, as a Christian there, in the past, as a Christian there, we were actually prosecuted. Our right was not guaranteed. Okay, and in some places in Indonesia, it is still like that right now. Okay, now this discussion actually come from this part C question, right? So the reason I picked this question is actually main because what I want to talk about why America is so great, and be grateful to be here. Okay, you may be the ones getting help right now from your government. At least our government, regardless the administration is Republican or Democrat, the president Republican or Democrat, we have a very good system that helps students a lot to survive in education. It's not perfect. Again, it's not perfect. But at the same time, it's much better than Indonesia. It's much, much, much better. Trust me. Much, much, much better. Okay. Can we be better? Yes, we can. Okay. But to say that the system is bad is overkill. Okay. Now, with these two, I set it up for you for part A and part B. I would like you to do this problem in 5 minutes plus 10 minutes break. So that's 15 minutes from now. We come back at 10:33. At 10:33, we will finish this problem and then we move to chapter 7. Okay, let me start. Probability that x is less than 72. That's normal CDF. Negative E99. Up to 72, the mean is 68.6, standard deviation 2.8. That will be, let me give myself some space here. That will be normal CDF, negative E99, up to 72. The mean is 68.6. Standard deviation 2.8. That is 0.88768. So the probability is very high that most male will be okay with this, the height of the doorway. Okay, but what happened to the average? The average, that will be normal CDF. Okay, negative E99, 72, 68.6. but this is 2.8 over square root of 100. That is 1. Okay, so the average of 100, the average height of 108 men is for sure less than 72 inches, which is 6 feet. Okay, but there will be approximately 12%. There will be approximately, I should say plus minus, approximately 11.2% of male passengers needs to bend. Okay, so if you have 100 male passengers, approximately 11, give or take some, will need to bend. Okay, will they need to bend a lot? Not sure. I don't. That depends on, right? Okay, but I think that will be fine. Okay, I think that will be fine. But considering A and B, which is more relevant? Well, the one more relevant is part C. Part A. Part A is more relevant. Okay, of course, most of these people, I believe, if not all, most of them will be willing to bend a little bit. They may realize that their height is actually above average, right? Okay, so not only the doorway of this plane, other place also they need to bend already. Okay, so I think they don't mind, but simply because the average is less than 72 doesn't mean some people should be ignored, okay? Even though they're definitely the quote unquote the minority in this airplane of 200 passengers, only 12 of them, give or take, need to bend, but still we need to consider their comfort, okay? Okay, imagine instead of bending down so that their head not hit the top of the doorway, imagine if that's the seat, right? Okay, such that imagine if when they sit, they need to actually, their knee actually hit the seat of the passenger in front of them. That is very big discomfort along the trip, right? Okay, yeah. The good thing is like, I think they don't mind to bend a little bit when they get into the airplane, okay? When they get into the airplane. But if they need to bend for their whole flight, that's a big no-no. I don't think that will be good. Okay, part D. Why are women ignored in this case? Are they really ignored? Not really because they are ignored, but because the average height, women in general has less height. I don't think that's the right wording. Women's height in general is less. Is less than man's height. So I do not want to say women's height are ignored actually, okay, but because their height in general is less, so it won't be an issue for them as much as an issue for men. Okay. So you see that the majority should not rule, right? Okay, even though the majority should be respected, but doesn't mean minorities' right should be ignored. No, in this case, women is actually not ignored. Okay, but if it satisfies men's height, which is usually taller, then most of the time, then with that such height, women will be more will fit into the doorway. Okay, now that's for number 19. And the suggested homework you can see from the lecture. Okay, you can see from the lecture for the suggested homework. Oops, I'm sorry. I'm still here. Oh, shoot. I keep on telling the stories and I didn't realize that I'm still here. Oh, shoot. Oh, my bad. Okay, this is for part B and C, and then I think we talked about this earlier, right? Okay, I'm sorry. I totally forgot to change my screen. Talk so long already for a couple minutes. Yeah. Okay, yeah, so according to our computation, approximately 11.2% of male will need to bend. Okay, maybe just a little bit, so they should be okay. But it doesn't mean that's not relevant. Of these two cases here, part A is the more and more relevant. Okay, the majority of men will be okay. On average, their average height is less than 72 inches. So they will fit to go through the door without bending, on average. Okay, but part A is more relevant. Now, why women are ignored? No, the women are not ignored here. Okay, it's not because women are ignored, but it's more because we know women's height in general is less than men's height. Women tends to be shorter, right, compared to men in general, such that if men can satisfy that doorway height, then women will more likely than men satisfy the door, fit into the doorway. Okay, that's for number 19. Again, a good thing I checked. Yeah, good thing I checked the my screen. Okay, I'm sorry. Now let's go on to chapter 7. Chapter 7 will consist of 4 parts instead of only 3 parts. Okay, this is estimating parameters. Parameters are numbers or measurement we get from population. Now, what are the parameters we will measure? We will first measure the mean, and then the proportion, population proportion, and population variance. Okay, now that makes our consideration later on will be done in the following order. The first case will be estimating population mean with sigma known, population standard deviation known. Now, this part is not in our book. But it was in old edition of our book. Okay, recently, this part was taken out from curriculum. I don't know what's the reason, but I will still use that because it provides good template for the second case and the third case. What happens if we are estimating the population mean when sigma is unknown? Now, you can find this in section 7.2. Okay, now then the third one is estimating population mean, population proportion, that is in 7.1. And the last one will be estimating population variance that is in 7.3. Okay, that will be pretty much the end of the material for your test 3. Okay, now for the next 1 hour, I will go over approximately 1 hour. I will go over the first case. But again, that's not in our textbook. It's already in my lecture. Okay, it's already in my lecture, and I believe I did a very good explanation in my lecture. Okay, now estimating mean population mean with sigma known. Now let me repeat some key components of this. What we are going to do is basically constructing confidence interval for population mean. Okay, and it will be done in the following steps. Procedure. Always do confidence interval always construct confidence interval in this in 3 steps. It's always 3 steps. Okay, at least for the first 3 cases here. For the first 3, all 4 cases you will have 3 steps, but the first 3 cases have very similar 3 steps. Okay, the first step is consists of 2 parts: best point estimate okay, and the second part of that is critical value. The best point estimate for mu, this is mu hat, means the best point estimate for population mean, is equal to the sample mean. Okay, now again, please watch the lecture for today. Please watch the lecture for today. Okay, for the lecture video. For April the 23rd. Hold on, is it? Yeah, I think it's April 23rd. Okay, that's where I provide a lot more details, but here I give you the template and I will do examples. Okay, the template is step 1 consists of 2 parts, best point estimate. Second, because the sigma is known, we will use C critical. That's the best, that's the critical value. Okay, now later on, if sigma is unknown, then the critical value will use T critical instead. Okay, if the sigma is unknown. Part B, margin of error. Denoted by E, that is the critical value that we get from part 1B times the population standard deviation over square root of n. Okay. Now, later on, if the sigma is unknown, then what is the margin of error? The margin of error Instead of using critical value Z, we will use TZ. And instead of using population standard deviation, we will use sample standard deviation instead. Okay, but we will do that later on from problems in our textbook 7.2. Now, part 3 consists of 2 parts also. The first one is basically a routine, okay, administrative, is the declaration, confidence interval for mu will be the best point estimate minus margin of error less than mu less than best point estimate plus margin of error. Okay. Now, please memorize this procedure, which will happen if you do enough problems. Do not do it with other way when you are in my class. Okay, other teacher teach with their own template, but the template I give you here is the commonly followed procedure in practice. In other words, if you do a research later on, you do a survey, you do a poll, and then you need to give a report, then the report must be written this way. Okay, then the report must be written this way. Okay, let's start with an example. Because this material is not in our textbook, then I need to create my own example. I may pick problems from old textbook. I have my old textbook here, but let's start with an example that we can easily get for now. A less wordy one. For example, the first example. Okay, let's say we sample 35 students. It turns out that their average height is, let's say 64.7. Now we know that the standard deviation of heights for adult students, let's say is 2.1 inches. Okay, of course, these numbers are all hypothetical, but suppose we have this. We sample 35 students. The average height of these 35 students is 64.7 inches. And we know the standard deviation of students' height is 2.1 inches. Now we want to construct a 95% confidence interval for mu. Okay, now solution, we will do it in these steps. Step 1, what is the best point estimate? If I can only choose one number to be the best estimate, only one number to be the best estimate for student's height, that will be X bar, the sample mean, which is 64.7 inches. Okay, again, the mean can be any number. The mean can be any number. Now, the sample mean of these 35 students is 64.7. Okay, now if you ask me what will the population mean be, of course it can be more than 64.7, can be less than. In fact, choosing one number saying that our mu is 64.7 is very likely is wrong. Very likely the population mean of students' height is not 64.7. Okay, but the thing is, we cannot really tell if it is more than 64.7 or less than 64.7. In other words, even though we know more likely that 64.7 is wrong, the information we get at this point will make other choice even worse. Okay, so you can criticize as much as you want for this 64.7, but any other choice will be worse. Okay, let's say somebody say, well, it's supposed to be higher. How do you know it's higher? Or less than 64.7? How do you know? You have no reason, right? You have no reason to say that the mean should be higher or smaller. Okay, so if the sample mean is 64.7 and then the best point estimate you choose is something different, let's say 65, you will be more being criticized for that choice. Why? Because even though 64.7 is most likely wrong, but it is also the most likely to be right compared to other choices. Okay, so sometimes we as a member of society, we are very quick to judge other people without thinking that the alternative that usually we don't even offer, okay, without thinking that other alternative will be worse. So before you blame other people, why did you do that? Why don't you do this? Ask yourself first, will that be a good idea? Put yourself in that person's shoes. Okay, if you ask me for advice, I can say more, right? Thomas, if I'm in this situation, what do you think I should do? Then I can give you my advice, but I should not be the person who actively come to you and criticize your lifestyle. No, I won't do that. Other than what I need to teach you, statistic, I'm not a good judge and I'm not supposed to tell you what is right, what is wrong. In anything other than statistic and how you're supposed to study statistic. Okay, so going back here, even though we know the best point estimate 64.7 very likely is wrong, but other choice is worse. That's why we call that best point estimate. Okay, think of that like choosing your spouse. Like, think about choosing your spouse. Who should you date and marry? Okay, trust me, the person you date and marry will not be the perfect person. Okay, my wife is not perfect. And I'm sorry, she's not the most beautiful girl in the world. But why I marry her? Because she's the best I can get. Okay, that's what we mean by the best point estimate, not perfect point estimate. Okay, no. Okay, she is my best point estimate. Why? Because if I can choose only one person, she's the best choice I can get. Why? Even though she's not the most beautiful girl in the world, she knows that by a fact, right? Okay, but she's the most beautiful girl willing to marry me. Let's put it that way. Okay, of course, it's more than just beauty, right? Her attitude, her personality match me the best and still willing to marry me. Okay, there must be a lot of girls that have better attitude out there, but those girls, they don't even look at me. Okay, okay, that's the thing though. That's the thing. Okay, now that's part A. The second, how about the critical value? How to find the critical value? They tell us that the confidence level is 95%. It means we need to find the critical value such that the area in the middle of that critical value is 95%. So we need to find that C critical. This is the C critical we are looking for. Now that 95% is the area in the middle. Now, if 95% is the area in the middle, it means the remaining 5% that's missing from this 95%, the remaining 5% will be shared by two tails, and it implies each tail has area 2.5%. Okay, so the area to the left of this C critical will be 2.5% plus 95%. That's how we get the area to the left of that is 97.5%. So what is the C-score? The C-score will be inverse norm 0.97501. Now then you use your calculator. Inverse norm 0.97501. I get 1.95996. Now, in my lecture video, I provide more examples on how to find this critical value. Okay, now if you have not watched that lecture video, you just want to go ahead with this, fine. But along the way, when we do problems, I will do this critical value, maybe in the next 2 or 3 questions. Okay. Now, step 2, what is the margin of error E? Margin of error is the formula for margin of error. So that procedure there, you want to write it in your cheat sheet. Okay, that is the critical value times the population standard deviation over square root of the sample size. That's the margin of error. 1.95996 times 2.1 divided by square root of 35. I get 2.82551. That's the margin of error. So step 3. Always start with the declaration. Always declare. Okay, 95% confidence interval for mu. The average height of all students will be the best point estimate. Let me write down the formula again. The best point estimate minus margin of error less than mu less than best point estimate plus margin of error. So you can think of that as this. The interval we create is actually start from the sample mean, and then you plus margin of error and minus margin of error. Now, this will be the interval we are talking about. Okay, because this is best point estimate minus margin of error, and this is best point estimate plus margin of error. Okay, now the mu, okay, 95% of the time, if we follow this procedure, 95% of the time, the mu will be in this interval. That's what we mean by 95% confidence interval. The confidence is on the procedure. Okay, the actual mean will be in this interval with 95% confidence level. Okay, so if I use the numbers, now we will get 64.7, that's the best point estimate, minus 2.82551, less than mu, less than 64.7 plus 2.82551. The lower bound, this will be 61.87449. The upper bound will be 67.5 52551. Okay, now always do that in these 3 steps. Okay, let's do one more examples from me, and then I will take problems from the older edition of our textbook. Okay, example 2. Let's say we sample 20 people, 20 students, and the sample mean for the IQ is 107. Now we know standard deviation of IQ score is 15 in general, even IQ score for students. Now then, give me a second. Then construct, let's say 97% confidence interval for the average IQ score of students, let's say at West LA College, if these samples are from West LA College. Okay, so step 1, best point estimate will be X bar. Critical value will be, then construct the standard normal distribution. And I want to have 97% in the middle, which means the remaining 3% will be shared by 2 tails. Now the C critical, the critical value will have area to the left, 1.5% plus 97%. That's 98.5%. Okay, now then you will do inverse norm. (0.98501). That is 2.17009. Therefore, the margin of error will be the critical value times the population standard deviation 15 over square root of the sample size 20. I get 7.27870. Now then, the last step, declaration, 97% confidence interval for mu. That will be 107 minus 7.27870 less than mu less than 107 plus 7.27870. That will be 99.72130 less than mu less than 114.27870. Okay, this is the word. Now, what I will teach you next is how to confirm use our answer by calculator, but do not skip my 3 steps procedure that I require you to do and just use calculator. No, okay? What I will teach you next is how to confirm your confidence interval for mu with sigma known using calculator. Okay, note this is to supplement if you want to confirm, but not substitute. But not to substitute what I taught you earlier. Okay, you always need to show these 3 steps procedure. Your final answer may be checked, confirmed using calculator. And the way you punch your calculator will be as the following. You go to stat, and then go to test, and then you go to Z interval because your critical value is in Z score. Okay. Now then, because the number provided to you are in statistic, then you will enter the sigma, then the input will be stats. Okay, the input will be stats. You enter the sigma, you enter the sample mean, you enter the sample size, and then the confidence level. Okay, let me show you with calculator. Okay, using example we have from above. Let's say we use this example here. Okay, and you will see later on why calculator doesn't help to substitute, but helpful to confirm. Now we start from pressing stats, not distribution. No, you go to stat, and then you move your cursor to test, and then you scroll down to number 7. On my calculator here is number 7, the Z interval. Okay, now the input will be statistic, which means you will give them the sample mean instead of the raw data. Okay, the population standard deviation is 15. The sample mean is 107. The sample size is 20. The confidence level is 97%, but you need to write it in decimal, 0.97. And then you calculate. This is the output. Now, why I say this is not a good substitute? Because if you follow my 1, 2, 3 steps procedure, okay, you will have 5 decimal places in your solution, while calculator will give you only 3 decimal places. In fact, they always give you only 5 numbers, the first 5 numbers. Okay, so you see that if you use calculator, then you will get this number instead of my full 5 decimal places. And if you use calculator, you will get only up to 2 decimal places of what 5 decimal places you're supposed to provide. Okay, we use Z interval because the sigma is known. Therefore, we use standard normal distribution Z. Maybe I use this color. This C here relates to this Z interval here. Okay, we use the C interval because that's confidence interval. Okay, now let's try to confirm our answer in part example 1. Let's confirm our answer in example 1. Take a look on the calculator. We start all over, go to stat, test, Z interval, not C test, Z interval. The input will be the statistic where the sigma is 2.1. The mean is 64.7. Sample size is 35. Confidence level 95%, 0.95. Screenshot and put it there. Ah, sorry, not this one. Let me put it here for us to compare. Huh? Why I get different? Let me check my computation. Okay, let me check my number again. Did I punch anything wrong? Oh, good thing I checked. The population standard deviation is correct. That's 2.1. Sample mean 64.7. N is 35. Did I punch anything wrong? Yeah, from here I see nothing wrong. From here I see nothing's wrong. From my calculator. Okay, but maybe my number when I compute that it's incorrect. 1.95996 times 2.1 divided by square root of 35. Ah, okay. I make a miscomputation here. It should be 0.69572. Okay, so I fix this here, should be 0.69572, 0.69572. So the final answer should be 64.7 minus 0.69572. That is 64.00428. And 65.39572. Okay, so you see what is the purpose I teach you this checking, confirm your solution. And my mistake was not intentional though. I really make that mistake. Okay, good thing I check with calculator, right? Good thing I check with calculator, then I can fix it now. Okay, because my calculator it's like show something very different. So I go back and I check again. Oh, did I punch anything wrong with this? No, nothing wrong. Now, did I punch anything wrong when I compute this? It turns out that yes, I get it wrong here. Okay, but then once I fix this, notice that I get a more precise answer. I get a more precise answer compared to calculator. Okay, calculator again only give you 5 digits, while my answer is 5 decimal places. Okay, 5 digits compared to 5 decimal places. So my solution is more accurate right now. Okay, a calculator only to help us to detect if I make miscomputation. Okay, if my answer is very far different, like what I had earlier. Okay. Now, let me pick problems from internet, maybe. Okay, let's pick problems from internet. I randomly confidence interval with known standard deviation. Is there any example? You know what? Let's pick problems from YouTube. If you wonder how I usually get questions, right? Beside YouTube. Beside YouTube, I actually type something. Oh, you know what? Let me pause this one. Oh, okay. Let's do part A. Why not? So let's use questions from YouTube. Scores on exams are normally distributed with a population standard deviation 5.6. Sample of 40 scores has the mean of 32. Going back to our notes. Estimate the population mean with 80% confidence. Okay, so step 1. Maybe let's write down what we have first. Scores on an exam are normally distributed with population standard deviation 5.6. A random sample of 40 scores has the mean 32. So what is the best point estimate? That's X bar equals to 32. Okay, how about the critical value? The confidence level is 80%. So I construct a standard normal distribution with the area 80% in the middle. So confidence level always means the area in the middle is 80%. Okay, the remaining 20% is being shared by two tails such that the area to the left on the left tail is 10%. And area on the right tail is also 10%. Now the critical value here has area to the left 90%, right? Okay, so the critical value is inverse norm 0.9001. That's 1.28155. So 2, what is the margin of error? 1.28155 times population standard deviation 5.6 over square root of sample size square root of 40. 1.28155 times 5.6 divided by square root of 40. I get the margin of error will be 1.13473, such that my 80% confidence interval for mu will be 32 minus that, less than mu, less than 32 plus that. So it doesn't take that long, huh? That's 30.865327 less than mu, less than 33.13473. Now let's check using calculator. just to confirm that we don't make any mistake. Okay, oh, I use this one here. Okay, stats, test, C interval. And you don't need to show your calculated result on your test later on. Okay, just for you to confirm. Okay, but I teach you calculator just like what I said in the past. I teach you how to use calculator. One of the reason is such that if you do well in this class, hopefully you can market your skill to tutor. Okay, to tutor other students. Screenshot so that we can easily compare. So this is the answer from calculator. Okay, notice that we are accurate to, oops, that we are accurate to 5 decimal places instead of only 5 numbers. Right? So the answer I want is the one you do in 3 steps, not the result from calculator only. Okay? In fact, not the result from calculator at all. Now, how about if we see what's the result from the YouTube? Let's see, can we fast forward that? Oh, they do it in a long way. Hold on, let me stop here. Let me screenshot this then. So that you can compare what is the result with the YouTube. Okay. In this case, even YouTube has less accuracy. Notice that compared to calculator, calculator gives us 3 decimal places. The YouTube result only gives you 2 decimal places. But that's because they use table. That's because they use table. As you can see on the video earlier, they use table method. Okay, they use table method. The upper bound is actually, yeah. If you compare with the calculator result, then if they round it to 2 decimal places, it should be 13.14, right? But the actual number is actually 13.134 something. So if you round to 2 decimal places, then the YouTube result is actually correct. Should be 13.13. Okay, now that's for 7.1. A little topic, supplementary topic, which of course I asked in my test also, is the minimum sample size. Minimum sample size. Given confidence level, population standard deviation, and margin of error, can we find the minimum sample size? Suppose we want to construct a confidence interval, okay, but we don't know what is the appropriate sample size such that it fits into the required margin of error. Then you will use this formula. N equals to the ceiling, means you round up, of the critical value squared times population variance over margin of error squared. Okay. So let's say, for example, I think I will give you only one example here. And the thing is, we don't have calculator for this. Unfortunately, we don't have calculator for this. Okay. For example, find the minimum sample size required so that the error to be less than 0.5 with confidence level, let's say 98%, if the population standard deviation is, let's say, 15. Let's say, for example, we know that population standard deviation of adult IQ score is 15. And we want to estimate the population mean, the mean of IQ score of all ELEC students. Okay, now we want the error to be less than 0.5. We want the error to be less than 0.5. If the confidence level is 98%, then what is the minimum sample size? The first step will be to decide what is the critical value. If we have 98%, confidence level 98%, means the area in the middle is 98%. The remaining 2% being shared by two tails, each tail is 1%. So the critical value with area to the left, 99%, right? This will be inverse norm, 0.9901. I think that's 2.32 something. Let me see. Almost 3.3, 2.33. Yeah, 3267. I'm sorry, 32635. Now then, that's the first part. Then the second part, the minimum sample size will be 2.32635 squared. Don't forget to square it. Population variance is 15 squared. That's the standard deviation being squared over the margin of error 0.5. So you want to be very accurate. You want to be very, very accurate, that you are off by at most 0.5. So 2.32635 squared times 15 squared divided by 0.5 squared. I get 4,870.71, but I need to round it up. So the minimum sample size will be 4,871. That's the minimum sample size. Okay, now minimum sample size, we don't have the formula that we can use from calculator. So you have to memorize this formula. You have to memorize this formula. Okay, since it is open book, open notes, then I would like you, I think you should actually write this down on your cheat sheet. Okay, don't depend on your notes only. You need to summarize your work. Okay, now let me go on to 7.2. This is in the book. 7.2, this is estimating mu with sigma unknown. Here's the template. Confidence interval for mu with sigma known. If the sigma is known, then the steps will be first, best point estimate will be mu hat equals to x bar. The best point estimate for population mean is the sample mean. The critical value, we use z-score. Now, then the margin of error E is equals to z-score, the critical value, times population standard deviation over square root of the sample size. The third step is the declaration confidence interval for mu, which is given by best point estimate minus margin of error less than mu less than best point estimate plus margin of error. That's what we did earlier in the previous part where sigma is known, but that section is not in our textbook. So I have to teach you, I need to steal some time and teach you that separately. Now, so what happened if we want to construct confidence interval for mu if the sigma is unknown? So we will use population standard deviation instead. Okay, in place of population standard deviation, we use sample standard deviation, but our critical value, okay, will be replaced by, instead of standard normal distribution, we will use T distribution. Okay, so what will change in our original template, the one here? We will use T critical instead. And therefore, our margin of error will be, the critical value T critical times sample standard deviation instead of population standard deviation over square root of n. Okay, the one changes, I write it in different color. Everything else stay the same. Okay, everything else stay the same. Now let's do one example and I will show you how to use calculator for that. Okay, show you one example and how to use calculator. And then we do problems, more problems from our textbook after the break. Give me a second, let me look for problems from 7.2 in our textbook. Let's say we do problems number 9. This is from our textbook 7.2, number 9. Use this summary statistic given in exercise 8, where the sample size is 205 and the sample mean is 30.4, sample standard deviation is 7.1. Use a 95% confidence level. Okay, now you don't need to worry about the follow-up question. Are the results very different from those found in example 2 with only 15 samples? Yeah, if your samples is very far different like this, then of course you expect the confidence interval will be very different, because the larger the sample size, the more accurate our answer is supposed to be. Okay, there's strength in number, there's accuracy in numbers, right? Okay, so solution, let's write down what we have first. The sample size is very big, 205. The sample mean is 30.4. Sample standard deviation is 7.1, while confidence level is 95%. Okay, so step 1, best point estimate is x bar equals to 30.4. How about the critical value? We will use T critical. Now, what is T distribution? T distribution is very similar to standard normal distribution. It's bell-shaped, symmetric around the mean, but it is it's flatter. It's not as, the peak is not as high as normal distribution. Now we need 95% in the middle. Okay, now then this is our T critical here, such that the area to the left is the remaining one tail area plus 95%, that's 97.5%. Okay, now the T critical later on will be inverse T, not inverse norm, inverse T. It's inverse T, not inverse norm. Not normal distribution anymore, but T distribution. The area to the left, 0.975. Okay, and it will be followed by only one number, that is the degree of freedom. Okay, what is the degree of freedom, Thomas? Degree of freedom is, in this case, and actually in this class, just say that in this class, the degree of freedom is always n minus 1. 1 less than the sample size. Calculator. How do we find that? That's inverse norm, usually below inverse T, which is usually below inverse norm. Okay, area to the left, 0.975. Degree of freedom is always 1 less than sample size. Okay, 1.97166. So the critical value will be 1.97166. Oh, then how about the margin of error? The margin of error will be 1.97166 times sample standard deviation, that's 7.1 over square root of 205. So this margin of error will become very small because the sample size is very big. I get 0.97772. Such that my confidence interval will be, so 95% confidence interval for mu will be the best point estimate, 30.4, minus margin of error, less than mu, less than 30.4 plus 0.97772. That's 29.4228 less than mu less than 31.37772. Calculator. We will use stat test, but not C interval. We will use T interval. Okay, we will use T interval. Let me move it here. The mean is 30.4. Sample standard deviation is 7.1. Sample size 205. Confidence level 95%. Okay, again, if you just use calculator, you won't be as accurate as I do. Okay, so to summarize the calculator, to confirm with calculator, you go to stat, and then test, and then T interval. Okay, and then you go on from there. Okay, now I will give you a break together with some problems from our textbook I would like you to do. Let me ask you to do number 11 from your textbook. You don't worry about your the follow-up question. So let me screenshot that to us here. Number 11. Okay, let me write it down. So the sample size is 106. The sample mean is 98.2. Sample standard deviation. Okay, so we know it's from sample because of the following. Okay, the data set includes a sample of this. Now this sample has this mean and this standard deviation. So we know this standard deviation is from sample, not from population. Okay, now we need confidence level at 95%. Now I want you to do this. Okay, I want you to do this it should take you less than 10 minutes though. I think even 5 minutes should be good enough. Okay, and then I will give you 20, 30 minutes long break for the day. So we will come back at 12:25, let's say. Okay, with this question number 11 is done. With question number 11 is done. Let me see if we can have more. Oh, after that we will do number 16. Oh, I do it. We do it later. Yeah, we do number 16 or 17 later. Yeah. Okay. Let's do number 17, number 11 first, together with your long break. So either you take your break first and then you work on this, or you work on this and then take your break. Now this question should take you no more than 10 minutes. If you do this in recording, this should not be more than 10 minutes. Okay, talk to you later. Okay, let's start again. So step 1, best point estimate, x bar equals to 98.2. critical value, because we don't have the population standard deviation, we have sample standard deviation. Then we use T critical, 95% in the middle. That's the confidence level, right? So the remaining 5% being shared by two tail, such that the area to the left of that 3 critical will be 97.5%. So the calculator notation will be inverse T, not inverse norm, 0.975, and degree of freedom is 105. Okay, again, the degree of freedom is 1 less than the sample size. Step 2, oh, what's that? This the T critical, therefore equals to inverse T .975 is the area to the left, degree of freedom 105. I get 1.98282. 1.98282. So the margin of error will be 1.98282 times 0.62 over square root of 106. Which will give me 0.11940. Therefore, my 95% confidence interval for mu will be the best point estimate 98.2 minus 0.11940 less than mu less than 98.2 minus plus 0.11940. So this will be 98.08060. This is 98.31940. Calculator, just to confirm, right? Stats test T interval. The mean is 98.2. Sample standard deviation 0.62. Sample size 106. Confidence level still 95%. This is what we get. Okay, so if we confirm the left bound up to 3 decimal places is correct, the upper bound up to 3 decimal places is correct. Okay, so we can confirm that we did it right. Okay, now the next question, we add a new flavor in that. For the next question, let me do number 17. Number 17. In a study of speed dating conducted at Columbia University, male subjects were asked to rate the attractiveness of their female dates, and a sample of the results is listed below, where 1 being not attractive and 10 being extremely attractive. Now use 99% confidence level. So the confidence level is 99%, but that's all we have, huh? Now, instead of giving us the statistic from the sample, they give us the raw data. Okay. Now here we have how many, what is the data, the sample size? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So n equals to 12. N equals to 12. But we need X bar and we need sample standard deviation, right? We need sample mean and sample standard deviation. Now, how will we do that? How will we do that? Then we need to remind ourselves how to compute sample mean and sample standard deviation, right? Okay, so solution. The confidence level is 99%. The n is equals to 12. Now you need to find the sum of the data and the sum of the square of the data. Okay, we use our calculator. Oops, sorry, I punched the wrong one. Am I still at? Okay, yeah, so I will punch in the sum of x, that's 7 plus 8 plus 2 plus 10 plus 6 plus 5 plus 7 plus 8 plus 8 plus 9 plus 5 plus 9. The total is 84. The sum of the data is 84. Now, how about the sum of the square of the data? So 7 squared plus 8 squared plus 2 squared plus 10 squared plus 6 squared plus 5 squared plus 7 squared plus 8 squared plus 8 squared plus 9 squared plus 5 squared plus 9 squared. That's 642. Okay, so the sample mean will be 84 over 12. I think that's 7, exactly 7. And the sample variance will be sample size times the sum of x squared minus the sum of x being squared over 12 times 11. That's 12 times 642 minus 84 squared. That's 648 divided by the product of 12 times 11. 4.90909. So S, the sample standard deviation is 4.90909. Oh, I'm sorry, that's S squared, huh? So the sample standard deviation will be the square root of that. The square root of that number is 2.21565. 2.21565. Now, then we will use this information later. Okay, so this is our first step. Let me not to use a line there. This is our step 1. Part A, where you get the statistic from the sample. Okay, now then we will use this number later on in our data further. But let me interrupt intermezzo. We can plug these numbers into calculator. Into our calculator. to get all of this, the sum of x, the sum of x squared, the x bar, and the s. Okay, and how do we do that? We will go to stat. We'll go to stat. Okay, and then edit. And then you input the data. Okay, but you may want to clear the data in case anything in your calculator. So you to clear data, to clear previous data, you go to stat and then clear list. Let's say, for example, on my calculator here, if I go to stats and I see the edit, I have some data in my list 1 and list 2. Okay, I want to clear them. How do I clear them? You go to stat and then clear list, right? And you want to clear list 1 and list 2. Now, list 1, L1, is the second of 1. That's list 1. And list 2 is the second of 2. So L1, you clear L1. If you want to clear L2 at the same time, you put comma, L2. Then when you go to stat, edit again, you see it's already clean. Okay, that's to clean. Now I will put in this number: 7, enter, 8, enter, 2, enter, 10, enter, 6, enter, 5, enter, 7, enter, 8, enter, 8, enter, 9, enter, 5, enter, 9. Now make sure that in the next line you will have L113, which is still blank. It means so far you already enter 12 data. Now to compute, you go to stat again, calculate 1 var stats. Okay, the list is L1. Frequency list, leave it NP, clear. That's what we get. Okay, so to compute, so you after you input and then you compute, you go to stat, calculate, and then 1 var stat. Okay, 1 var stats. And the result will be as the following. So you see the x bar is the same. The sum of x also the same. Sum of x squared also the same. And our s is also the same. Now, if in my test I say use calculator to find the mean, sample mean and sample standard deviation, if I specifically say use calculator, then it means you just give me this number right away. You use your calculator and just give me this number. Okay. Now, if I don't say use calculator, or sometimes I even specifically say show your work, then you need to show me this. Okay, you need to show me this. However, notice that you never show the work for this guy, right? You never show the work for this guy. So what I suggest you to do is you plug in these numbers here to your calculator the way I showed you earlier. Okay, and you get that sigma x and sigma x squared. And then you can compute this easily and confirm with the answer you have from your calculator. Okay, now next, from here, from there, then we construct the confidence interval. Okay, step 1, best point estimate is X bar, which is 7. Okay, and then critical value, the T critical, the confidence level is 99%. The remaining 1% is being shared by both tails, such that the T critical have area to the left, 99.5%. So T critical will be inverse T, 0.995 degree of freedom, 1 less than the sample size. That is inverse T, 0.995 degree of freedom 11. It's 3.10581. 3.10581. So second step, margin of error, 3.10581 times 2.21565 over square root of 12, which will be 3.10581 times 2.21565 over square root of 12. That's the margin of error is 1.98649. So 99% confidence interval for mu will be 7 minus 1.98649 less than mu less than 7 plus 1.98649. So 5.01351 less than mu less than 8.98649. I kind of like just automatically do all of this because it's just the procedure we did before now, but some more things to show you. Okay, in the past, we confirmed this, right? Okay, we go to stats, test, T interval. Sorry, stat, test, where's my T interval? Yeah, T interval, and then, but the confidence level is 99%. So this is what we get. Right? Okay, and notice that it is accurate to 4 decimal places. In other words, our way of doing it is more accurate because we keep 5 decimal places. But I want to show you one more thing. What is usually done in other textbook, with other instructor, they don't even care if you know how to show the work. Okay, they just ask you right away, oh, what is the confidence interval, right? Okay, without you showing any work. So those students will just use calculator. Okay, notice that we already plug in our data in list number 1. Okay, now, suppose I want to use that data and perform T interval, the confidence interval for this mean confidence interval for population mean with the data given to us. So instead, you will click on this data and the input will change. Okay, what is your list? Then the list will be L1, right? Second, L1. How about the frequency list? You can leave it empty or you leave it as 1. Okay, but don't make it 0. Don't make it 0. Either you make it empty or make it 1, but don't make it 0. Okay, and then confidence level is 99%, click enter, boom, that's what we get, which happens to be exactly the same with what we have earlier. Okay. Maybe let me change something, because actually, according to our number, this when we did the stat earlier, the sample standard deviation was 2.21565. That's the number we used earlier. That's the number that we used earlier. Oops. Okay, this is when you do stat, calculate, t interval, and then data, whatever list you use, the frequency is frequency list. Either you leave it empty or make it 1, and then you enter the confidence level. This is when you do stats, calculate, t interval, and then you use stats. So you need to enter what is the X bar, what is the sample standard deviation, what is the sample size, and what is the confidence level. Okay. Now let me ask you to try one more question using the technique. Give me a second. Oops, I happen to scroll out way too far down. Number 19, mercury in sushi. Suppose another instructor, if you happen to take this class with another instructor and they give you this question, and all you need to do is to construct a confidence interval. So you don't need to show work at all, right? Okay, with my class, I need you to show me the work. Okay, so suppose you have this data. Okay, and then you need 98% confidence interval for the mercury in sushi. Okay, with n equals to how many? There are 7. And the data are given there. Now, in my class, I need you, suppose I ask you to do it in full, right? So the first part you need to get is n equals to 7. You need to find the sum of x and the sum of x squared. Okay, you need to get that. And then using that number, you find X bar and sample variance. And therefore, later on, you will get sample standard deviation. Okay, how will you show the work? Then let me plug in data. This time, let me plug that into list number 2. Okay, 0.56 is the first data. The second data, 0.75. Make sure you type it correctly though, because anything wrong, the whole work will be wrong. And you have no way to check that anymore. 1.25, 0.54, 0.88. Now then I go to stat, calculate one var stats. Right now I need to change this to list number 2, not list number 1 anymore. Okay, so this is my data, my statistic. Okay, but you still need to show work for Thomas, right? So how will you show the work? You will write it this way. You see that the second row, you have 5.03. That's the sum of x. And the third row, the sum of x squared, 4.4171. Now, how about the x bar? Then you pretend you compute it, 5.03 over 7, right? That will be 0.71857. You can use your calculator to compute though, to confirm. That's 5.03 divided by 7. Do you get the same thing? Okay, now how about the sample standard deviation? Sample standard deviation will be 7 times 4.4171 minus 5.03 squared over 7 times 6. 7 times 4.4171 minus 5.03 squared divided by 7 times 6 is 42. That's 0.13378. 0.13378. So the standard deviation is the square root of that. Apply square root to that. I get 0.36576. 0.36576. Then you look at your screen again, but you don't show this to me, okay? You need to show this instead. This is the one you show me instead. Okay, but at the back of your mind, you know that you can use calculator to confirm your answer. Okay, now then, once you're done with that, you can start the procedure. Best point estimate, X bar equals to 0.71857. Second critical value, that will be inverse T 0.99. Oh, how do you get that 0.99, Thomas? Well, because the confidence level is 98%, right? The remaining 2% is being shared by two tails. So this T critical must have area to the left, 99%. Okay, then you use your calculator, you do inverse T, area to the left, 0.99, degree of freedom is 6, not 7. 3.14267. 3.14267. So margin of error will be 3.14267 times 0.36576 over square root of 7. $3.14267 times 0.3657 divided by square root of 7. That will be 0.43446. 0.43446. So the 98 confidence interval for mu will be best point estimate was what? 0.71857 minus 0.43446 less than mu less than 0.71857 plus 0.43446. I get 0.24, I'm sorry, 0.28411 less than mu less than 1.15303. So that's it, we are done. To confirm, you go to stats, test, T interval. Now you use the data from list number 2. Okay, the frequency is 1. The confidence level was 98%, 0.98. Dum, dum. Okay, so the lower bound, they happen to give 5 decimal places, right? But the upper bound, they give only 3 decimal places, while I give 5 decimal places. Okay, that's for up to 7.2 now. I think I will stop here, but let's take a look first on what will happen next week when we start, so that when you study, you know what you need to be aware of. Now, 7.1 is estimating population proportion P. Now, if you remember the template, step 1, best point estimate for mu hat is X bar, right? Okay, now here, when we are estimating P, yeah, this was estimating mu. Now, when we are estimating P, then the best point estimate becomes P hat, which is basically the sample proportion. Okay, now the critical value, when we are estimating mu with sigma known, we use C-score, standard normal distribution. We will still use standard normal distribution when we are estimating population proportion. So nothing changed there. Okay, how about the margin of error? Margin of error was critical value times sigma over square root of n, right? Now it changed a little bit. The margin of error will be equal to critical value, the same method, times square root of p hat q hat over square root of n. So you replace the sigma by square root of p hat q hat. Now, then later on you will see this formula is basically becomes, they put the square root together. If p hat is sample proportion, q hat is p hat minus 1 minus p hat. Okay, so step 3, the declaration confidence interval for mu, where the best point estimate minus margin of error less than mu less than best point estimate plus margin of error. Now the version for population proportion will be confidence interval for P. So the one change, I make it in red. Okay, and that will be P hat, the best point estimate, minus margin of error less than P, because we are estimating P now, not estimating the mu, less than P hat plus margin of error. So that's the change. Okay, so the only new stuff for you here is finding the p hat, the sample proportion. That's the only thing new. Everything else actually just the same. Okay, that's the only thing you need to compute. Now, if we need to use calculator to check using calculator, you will use stat, then calculate, and then that will be, let me see, that will be 1 proportion z interval, 1 proportion z interval. That's what you will use. Okay, I believe in my lecture video, I cover that quite extensively. So you can already work on this problem using that video. I just try to show you that there's nothing really new in this 7.1, except that we change the x bar becomes p hat. Okay, now let me do one problem and then I go home. I'm at home right now and then I log off. For example, suppose we want to estimate what proportion of our population already get vaccinated, fully vaccinated. Okay, so we do a sample of, let's say, 1,024 people, and we found that actually 415 of these 1,024 people, a sample of 1,024 people are vaccinated. Now, suppose we want to construct a confidence interval for population proportion already vaccinated at 95% confidence level. So how do we do that? Best point estimate, that's sample proportion, which is 415 over 1,024. That is 0.40527. Critical value, that's C critical, 95% means the area in the middle is 95%. the remaining 5% being shared by two tail. So the critical value must have area to the left 97.5%. Inverse norm 0.97501. It's standard normal distribution. So the mean is 0, standard deviation is 1. That will be 1.95996. 95% confidence level is very, very common in being used in statistics, especially for social sciences, such that I basically memorized that already. And it would be nice if you memorize that important Z-score also. Margin of error, therefore, will be 1.95996 times square root of P times Q hat. P hat, Q hat. Oh, what is Q hat? Q hat is 1 minus P hat. That is 1 minus 0.40527. Practice, practice, practice. Okay. When I saw how you did your tests, I noticed something that a lot of you don't have. You didn't practice enough, such that you spend more time in studying during the test. Okay, no, you need to practice. Okay, you need to practice. Q hat is something that you should have known that even from binomial distribution, right? But if you don't really practice, you don't even know what that means. And you will keep on flipping your pages, your notes, just to find out what is Q hat, right? So basically you burn your valuable time in your test for something you should have known even before the test. Like during the test, you should apply what you know. You just apply the procedure. You are not learning how to apply the procedure during the test. You apply the procedure, that's not the time you learn. And the notes, the cheat sheet, the textbook is there for you to confirm if you already use the correct formula. But if you actually try to multitask learning and applying during your test, of course, you don't have enough time. Okay. So 1.95996. Oh, yeah, let me show you how to use calculator. Okay. 1.95996 times square root of, you see, they put it under square root right away, 0.40527 times 0.59473 divided by 1024. Boom. 0.03007. 0.03007. So 95% confidence interval for P will be best point estimate 0.40527 minus margin of error 0.40527 plus 0.03007. This will be 0.37520 less than P less than 0.43534. Now, last thing, to check with our calculator, you go test 1 proportion C interval, 1 proportion C interval. The X is 415. The N is 1024. Confidence level 95%. Calculate. Boom. That's what we have. Okay. Last topic minimum sample size issue. Given the confidence level, margin of error, and p hat, okay, usually that's the pass sample proportion. What is the minimum sample size? The formula will be critical value squared times p hat q hat over margin of error squared. Okay, I will give you example on this next week. So call this 7.1a. Okay, however, if p hat is unknown, then use p hat equals to 0.5. If p hat is known in interval, let's say the proportion of people vaccinated is known to be between 30% to 40%, but we don't know precisely. And let's say 30 to 40%, then use p hat in the interval closest to closest to 0.5. Okay, but we will work on that next week. What we will do next week will be, this is what we'll do next week. Next week, we will do 7.1b, and then 7.3, and then Bayes' theorem. Okay, and the extra time we have, hopefully we have extra time, we will go over one old test 3. Okay, we will go over one old test 3. Now I will post, let me post it now. I will post the test for fall 2020 Math 227 test 3 for you. Okay, I will post that fall 20 last semester's test 3 on our discussion board today. Okay, then see you next week.